Good morning, everyone. I'm TJ, and today I will teach you how to do 1D meshing, 2D meshing, and 3D meshing of a cantilever beam. So I will show you how you can model a beam element, give it orientation, add beam cross-section properties, and how to post-process the results from a 1D beam mesh. Then I will show you how accurate these results become when you have bending loads on this beam. Then I will compare those results with what you get when you do a 2D mesh, if you mesh the mid-surface of this cantilever beam, and how you post-process, display the properties of the shell elements, and how the results become, how accurate they are compared to the beam mesh. And then finally I will show you a solid mesh, and then I will demonstrate how bad those TET4 elements are, which are sometimes the default choice in CAD systems. And I will also compare those results with what you get if you use a TET10 element mesh. And finally you can compare the results from the various simulations, and then you can conclude what to use yourself. Thanks. This is my beam model, and as you can see, it's a solid structure. So I created a sketch which was 100 millimeter wide and 10 millimeters high, and then I used the extrude command to extrude it 2000 millimeters in the global X direction. I made a solid model because I'm going to use both beam elements, shell elements, where I will use mid-surface meshing, and solid meshing as well, to compare the different element types. Before I make a FEM model, my first FEM model, I want to apply materials. And that's because I want to make 3 different meshes, and they will have the same material properties. And if I assign the materials to the geometry, I can avoid making the material model 3 times. So I go to Menu, Tools, Materials, Assign Materials. Then I get this menu. I can select my part, and then there is no local materials in my model, so I use library materials, and then I get access to lots of options. But I want a steel material. I could use steel, but it's a quite advanced material, and I only need the properties which are given for the steel rolled material. I can't use it directly, so I copy it. Give it my local name, steel beam, like this. Then I change the E modulus options here, and I want to use 206 940 megapascals. That's my E modulus. The Poisson ratio is 0.3, and that's okay. I don't have to bother about the density because this will be a static analysis. Then I press OK. And this is now my local material, which is applied to my structure. And that's fine, because then I can choose to inherit this material property to all my FEM models. Then I'm ready to create my first FEM model. I go to Application, Pre and Post. This is an NX11. And then I select my beam part, and I create new FEM and simulation. I want to create the idealized part because this geometry is obviously so simple, so it's not needed to simplify in any way. And then I got the setup for this solution, and the only thing I will do now is to go to case control, and I will change the output requests, and I will apply or ask for force results. They are on here, but they might not be the default choice in your setup. Okay, and that's my structural output request, because beam and shell results, stress results, they are calculated based on element forces, so you need those. Okay. Then you can see that my FEM model is the active part, and I will start to create a 1D mesh here. And then I choose the beam element, and I can select the edge here, which is perfectly aligned with the x-axis. The number of elements, I can start with just making one element. It will have some effects on the results when I display them, but the results will still be accurate, as you will see. I can automatically create a collector, but I want to make my own new collector. And I will make a beam property, create physical property here. And I need a section, and this section is going to be constant. So I will create a constant section. So I go into the section manager, and here I can create a new section. I don't want a rod section, I want a section looking like this. So I choose a bar because it's a solid section. Here you see dimension 1 is the width, and for me it's 100 millimeters, and dimension 2 is the height, and it's going to be 10. And you should notice that the local y-axis now is going in that direction, the short direction of the beam, the height, which is the global z direction. And I could also give it a proper name. Instead of bar 1, I could call it bar 100 times 10, so it's easy to recognize. And I can preview it here. Here you see a preview of my section. It looks good. And I press OK. So that's my new section, and I close, and it's automatically added as my fourth section. And here you see material properties. I could choose steel beam, but inherited is okay, because then I will use the same materials as those materials I applied to the CAD geometry. And if I change it in my CAD model, it will automatically be updated here. So that's okay. Then I made a collector, and I can also give the collector a good name, like 100 times 10, which is the dimension of my beam element. And the beam property is beam P-beam L1. That's it. And now I can mesh it, and it will be just one beam element. You can't really see it, so we can change the appearance of this one. We can go to the 1D mesh, and I can edit display. And here I can choose to, where do I have the option to show display section? Solid, like this. Apply. Okay, so here you see my section, but you can also see that the orientation is not correct. So I have to do it in another command, edit mesh associated data, and here I give the orientation vector. And you should remember that the local y-axis of the beam element should go in the global z direction. So I can choose the z direction, or I can simply choose this edge, like this. Okay, so now you can see that my beam has got the right cross-section properties, and it also has the right orientation. Now it's a bit confusing to see the solid here, so I can switch it off. I can turn off the polygon geometry. So that's my beam element. And now I can activate my simulation. I choose my sim file. Well, yeah, we do so, make work part. And then I need the load and the boundary conditions. First, we can apply the constraints, new constraint, fixed constraint. And let's keep it clamped in this end. It's a cantilever beam. Okay. That's now my fixed end. And now I want to apply a load, new load, force, and I can apply the load at the end of the beam. And this load is going to be 50 newtons. And I want to apply the load in the global z direction, upwards. And I press apply. So now I have completed my model. I have applied the load, the boundary condition, and I'm ready to run the simulation. Then I go to solution 1 and I just click solve. I accept the model setup check, and the solution should only take a few seconds. Completed. And I can check the results. No errors or warnings. Then I go to the results tab and I double click, and I want to check the displacements first. And according to the analytical calculations, the displacement should be 77.3 millimeter in the set direction. So let's check. And this looks quite good. I could animate it. So we can conclude that the results are correct, but the actual shape looks a bit different. And that's because I'm only using one element here. And the line between the two nodes will be a straight line, even if it's not so in the real life. But the end displacement will be correct. But it looks like the clamped end is having an angle here, which is not correct. But we can also check the stress results, and then I go to applied force or stress element nodal, and I can choose sigma xx. And here you see it's minus 60 megapascal, and that's because it gives me the results on the upper end of the beam, which is in compression. But we can also use a tool in NX, beam cross-section view, and then I can choose the clamped end and press preview, OK. And here you see the results. You see that you have a compression stress, which is 60 megapascal on top, and you have a stretch, which is 60 megapascals at the bottom. And that's perfect. It's correct. But in order to display the results correctly, you have to actually go back to the FAM model, make it the work part, and you have to create a new mesh, and instead of one element, you need to create 10 elements, for example. Like this. Now you see that you have 10 elements along the length of the beam. And then we can activate the simulation file again, make work part, and run another simulation. But before you run the new simulation, you actually have to apply the boundary conditions and loads once more, because if you notice, we created a new finite element beam mesh, and what happens then, if you go to the sim file, you will see that the constraints are not active anymore. So we have to apply the constraints once more to the beam node at the clamped end, and we have to apply the load, static loads here, again to the node at this end. So now you see that the forces and the loads are correct, and we can run the new simulation and check the results again. Then my second run is completed, and I can check the results with 10 elements. I choose set deformations, and let's align the beam so we can see it from the side. And now you see that when we have more nodes, we can capture the deformed shape even better. But the maximum displacement, tip displacement, is still the same. It's 77.3 millimeter, which is perfect. It's what you get if you do an analytical calculation, which makes sense because both analytical methods and beam formulations are pretty much the same. So what you can see here is that if you have bending forces, torques or moments, and shear forces as well, then you can get really accurate results using beam elements for structures like this. The next thing I will do is to use a shell element mesh to see how well I can capture the same deformations and stresses. Then I made my beam part, my working part again, and I'm still in the pre and post application. And the next thing I will do is to create a mid-surface by phase pairs. And this is my command that I will apply. And I choose my solid part here. And the thickness ratio defined here is the default values, and they will work fine. If I click now on the automatic create face pairs, you can see that I will get a mid surface here. Here are other tools which I don't have to apply right now. And here is one option, hide solid body upon apply, and that's okay. So now you see that I don't have a 3D solid model anymore. I have a 2D surface, which is my mid surface. The next thing I'll do is to go and create new FEM and simulation. I press OK. The default choices are OK because I don't want to create an idealized part. And also I have my structural output requests. They are still here, so I will get my forces which I need in order to calculate shell element stresses. And I press OK. Then I want to mesh the model, and I use 2D mesh. I can use the C-quad 8 elements as my element types initially. And I select this polygon face, and I use my lightning arrow to automatically define the element size, which then is 141 millimeter. And I create OK. So here I can create a new collector, and I can call it 10 millimeters, because that will be the element thickness. And I have to create the shell properties, create physical. I can inherit my material. I can also choose steel beam, but I can inherit it. And here at the default thickness, I would normally select 10 millimeters to be my thickness, because that is the thickness of the underlying solid. But I can keep it open because I will use another technique in NX to choose this one. So I only define the material here, and I press OK, OK. And then I'm ready to mesh it. Here you see my element mesh. But you don't see the thickness of the beam elements. So I have to do use a trick here. I go to the 2D collector. I select the mesh. First I use edit mesh associated data. And here the thickness source is default chosen to be a physical property table, but I didn't add any thickness there, as you noticed. So I use mid surface instead. And press OK. Now I've applied the thickness, but you can't see the thickness. So the next thing to do is to go to the 2D mesh, and I can edit the display, and I choose element thickness and offset, and I press OK. And now you can see that my elements got the right thickness, and it's also displayed as I wanted it. That should complete my meshing task, and I'm now ready to go to the simulation file, make work part. And again, I have to apply the same constraints as on my beam model. I use constraint, right click, and I use new constraint, fixed constraint. And now I choose the edge here, only the back edge, and I press OK. And you can see it's not visualized as crosses as it was for my beam model. But you can change the way loads and constraints are looking by use the edit display. And I can use expanded here, for example, or collapsed. And then you see it the usual way. The next thing is to apply the forces at the end. So I create new load, force. And again, I choose carefully the edge, which is along the end of the beam. And then I use 50 newtons upwards in the global Z direction. One thing you should notice is the distribution option here. If you use geometric distribution, you will distribute 50 newtons on all edges that you select. Total force will always be 50 newton. But if you choose total per object, then if you choose two edges, you will not apply 50 newton, but 100 newtons. So the correct here is geometric distribution. And I press OK. Here also the display is looking a bit funny, I think. So I want to change the display of my force. I right click, edit display, and I use collapsed, apply. So here you see the forces. They are distributed along the line. Then, if I haven't forgotten anything, I'm ready to run the simulation. Right click it, solve. OK. Then the solution is ready, and I'm ready to check the results. I can expand the results tab. And you see I still have the result for the first simulation, the beam simulation, but I go to Sim 2, which is my shell element simulation. And then first let's have a look at the displacements. I go to Set, and let's see here. The deformation looks quite good. The nodes capture the shapes. But you can see that the amplitude, the tip displacement, is 76.92, while the beam element results gave me 77.3, which meant this shell model capture the displacements quite well, but it's a bit stiffer than the beam element. The next thing we will check is the stress results. And then I use stress elemental nodal, and then I use sigma xx. And here you see that the results are quite okay. We see that we get 60.11 megapascal, and 60 is correct. And of course here you can also choose by set results. You can choose top or bottom. So if you choose bottom, you will see that the bottom stresses here are minus 60 megapascal. In the beam element results, we got the opposite, because in this example, we by an accident made a mid-surface that was twisted, so it points downwards and not upwards. But we can conclude that the results are correct. It's plus minus 60 megapascal, the bending stresses. So we can accept these results, and we can also do a simple benchmark with other element types to compare. Now I've created a shell 4 mesh, 4-node shell element mesh, with same default element size, 141 millimeters. And I didn't have to apply the loads and the constraints again, because I applied those on the geometry, the end edges of the mid surface. So now I run the simulation and I can check the results. And again I go to Sim 2, because that's my shell element model, and I can check the results. The set displacement, it's, as you can see, 76.89, which are really close to the shell 8 element results. So they are not perfect, but they are quite close to the beam results, which are accurate. Those were 77.3. So the shell elements are slightly stiffer than the beam element. We can check the results, stress results. We go to stress nodal. We check the sigma xx. And you can see those are not that accurate as for the shell 8 elements. And you can see also the distribution of the stresses. These are non-average results. They would probably be a little bit better if they were averaged. At least they will be smooth along the element borders. But the results are quite good. So the next step now is to go to back to the solid geometry and create a solid mesh and see how that will become. Now my geometry is again my working part, and in order to make a solid mesh, I have to press Ctrl W, and I have to display my solid bodies, and I have to remove my sheet body that I used for my shell mesh. There we are. So now again I create a new FEM and simulation. I press OK. The default choices are OK. And here I don't have to request the force results, but they are on by default, and that's OK. And now I'm ready to create the mesh. My FEM3 model, which is now created, is active, and I can use a 3D TET mesh. I select my body, and you see that the C tetra 10 element is the default choice here. And I use the lighting symbol to choose the element size, which is 48.3 millimeters. I won't use any of the other options here. I just choose the default settings and press OK. The automatic creation option could be used, but I go here and I select solid properties and I create it, and I use the inherited material as earlier. So now I've used the same material that I applied on the geometry 3 times. And I press OK. And now you see the mesh here. Quite large elements, and you know that you should really have 2 elements along the cross section over the thickness of the solid geometry, and here we have only 1. But let's see how the results become. You can imagine how many nodes and degrees of freedom we would have if we use a free mesh with 2 elements across the thickness here. And you can compare that with just using 1 beam element, which gave me 12 nodal degrees of freedom. We can check now the model size. We can go to finite element model summary, and we see here how many nodes we got. Total number of nodes in part is 2000 roughly. And if you multiply that with 3, which is the number of degrees of freedom on each node, we got 6000 degrees of freedom, or equations to solve. 6000 compares to 12 for the beam element. But let's see the results now. First we go to the sim3 file and make it the work part. Then we apply the constraints. We use new constraint, fixed constraint at the end here. Okay. And then we apply the load at the other end, which was a force load. And I use geometric distribution. That means when I enter 50 newtons here, it will be applied evenly on the end surface, like this. By the way, I've now made a serious mistake all over the video, because I never used the save command. And when you do this, you should press Ctrl S and save the models frequently. Something can happen. You lose contact with the license server or anything, so please save your model when you work. Okay, then I choose solution 1 and I run the solver. Okay. This shouldn't take much time. There we are. Okay, cancel. And then I check the results once more. I go to structural, and I don't want to see the sim2 results, but the sim3 results. So let's check the displacement for the solid elements. You see that the end-tip displacement for this element is 76.69. It's not bad. It's quite close to the beam element results. And you see the deformation, the deformed shape is captured well with all those nodes along the length of the beam. So that's okay. Let's check the stress element nodal, sigma XX. That's another story. Now you see that bending stresses here are 77.8 megapascal compared to 60 megapascal for the beam element and for the shell elements. So you can see that the solid elements, they are not capturing the bending stresses very well, even if we are now using a higher element, and the element size, the model size, is quite large. So now we will make another attempt, and now we will use the TET4 element, which is the default choice in some CAD CIA systems. We go back to the FEM model, make work part, and then we select the mesh 3D mesh. And instead of C tetra 10, we use C tetra 4. The same element size, and we press OK. And remember, this is the default choice for certain CAD systems that claim to be CIA systems. So let's now activate Sim3, make work part. We run the solution once more. And this should take just a second when the setup is, the model is checked and executed. So there is, now we have the results. And let's now see what results we get with the TET4 element. First, let's check the vertical displacements. Well, we see the shape looks promising, but watch those numbers. The correct displacement is 77.3 millimeters. And now we get a displacement which is 5.3 millimeters. We miss the correct results with a factor between 10 to 15, which tells me that TET4 elements are not able to capture bending loads or deformations at all. It's completely wrong. So you should notice this. So you can conclude that basically the TET4 element is just suited to represent the mass distribution of certain members in your finite element assembly, which are, let's say, not of any interest when it comes to displacement and stresses. They can only be used to represent certain inertias. If you have a battery in your engine compartment, that could be meshed with TET4 elements, if you don't know the exact mass. So this concludes my presentation. I've now showed you how to make a beam mesh, mid-surface shell mesh, and a solid mesh, and I've compared the results on a simple cantilever beam. And you can then see the results. And I will now show you some more comparisons in a matrix. Here you see some sample results. The TET4 elements with the default size, when I used the lighting symbol, was 48 millimeters. They gave me a deformation which is 5.1 millimeter compared to 77, which is correct. Absolutely rubbish. And the same with the stress results, the sigma x bending stresses. Even if you use a very dense TET4 elements, you see that the results are really bad. Both the deflections and stresses are far off. Even if the model size, the element size, the number of elements is really high and the total number of equation becomes high, the element shape functions are not able to capture bending at all. The TET4 elements give quite good deflections, nodal deflections. The bending stresses are not too good really, even if you use a very TET10 element mesh. But you see, even if you use a very coarse shell 8 element mesh, and also when we use the shell 4 elements, we got very good results. The deformations were like 76.9. The bending stresses were correct, both for the shell 8 and the shell 4 elements, as I showed you. When it comes to the beam elements, they are obviously the most efficient element type to capture bending in cantilever beams and those type of truss structures. The deflections get very precise, that means accurate, compared to the analytical calculations for any element size. We used 10 elements and 1 element. It gave the same results, and the stresses are absolutely spot on. And these are the analytical calculations, which I haven't shown, but they prove that the beam is the optimal element choice for this purpose. So, thanks for watching. I hope you had some interesting results here, and you know how to make shell elements with the mid surfaces and beam elements, and how to display the cross sections and give them a proper orientation.